When we solve a logarithm equation, it's very important that we check our answers. So let's go through this problem, and when we get our solutions, we're going to check both of them. So the first step you're going to do is a product property and combine the two logs into a product. So you have log of x times x plus 3. The next step is that you're going to rewrite this log as an exponential. So you're going to use the popcorn method. So we write it as 10 because we don't have a power, or I'm sorry, we don't have a base seen, so we understood that it's 10. 10 to the 1 equals x plus 3. Now this whole argument is the argument now. So we have x times x plus 3, which is going to become x squared plus 3x after we distribute. The next step is to solve this quadratic for 0. So we bring the 10 over and get minus 10. So now that we have our quadratic, we're going to solve. And note that this equation, this quadratic equation, is going to produce solutions to our log equation, but it might produce extra solutions too. So when we factor this, we get x plus 5 as a factor and x minus 2 as a factor. So when we solve, x equals negative 5 and 2. Now, going back to what we just wrote on the right, since we can produce these extra solutions, maybe, therefore we must check our solutions to check for those extra ones, which we call extraneous. So when we take negative 5 and we plug it back into the original, which is right here, you get log of negative 5 plus, but you don't even need to move on. You don't need to continue because you can't take log of negative 5. So negative 5 cannot be a solution. So then we check, okay, I can put 2 in here. I can take the log of 2. Then when I plug it in here for x, I get log of 2 plus 3, which is 5, which is also good. So 2 is our solution. Negative 5 is not. So because of this, you always need to check your solutions. Also recall the uniqueness property from exponentials. Well, we also have the same uniqueness property of logs. So if we have a log with a base equal to another log with that same base, then the two arguments, m and n in this case, are equal. So looking at this SAT problem, to put them together, well, putting them together on this left side, combining them is the first step. So that gives us, with the quotient property, gives us log base 2 of 24 over 3, which is 8, which is equal to log base 2 of, log base x, we don't know what x is, of 27. Now, because the uniqueness property says that the bases, if the bases are the same, then the arguments are the same. Well, because of that property, we can get rid of the fact that this x is not going to be 2, because 8 doesn't equal 27. So now we need to solve for what x is. So if we look at this left side first and say, okay, well, let's say that y equals log base 2 of 8, then we can rewrite it, popcorn it, and say 2 to the y equals 8. So what's y? Well, y equals 3 then, because 2 to the third is 8. Well, if this whole thing equals 3, then we can write that log base x of 27 equals 3, because the two sides are equal. So then again, we rewrite it as an exponential, and we have x to the third equals 27. Well, what to the third gives you 27? 3. So x must equal 3. So we're going to solve this log at the bottom the same way. We have two logs that are base 10, so the two arguments must be equal. So we can now use the uniqueness property and say that 2x minus 3 equals 3. Well, if I add 3 to the other side, I get 2x equals 6 and x equals 3. But we have to make sure that x can be 3 by checking it. So If I plugged in 3 right here, I would get the log of 2 times 3, which is 6, minus 3 of 3, which is good and happens to also equal the other side. So this is our solution. It is not extraneous. Okay, so when we solve logarithms, there's a couple general rules. You need to first combine logs to get no more than 1 log on either side. So we need to use those properties and put any addition problems or subtraction problems together. You remove the logs if you're using the uniqueness property, saying the 2 arguments are equal, or rewrite it in exponential form, which is like the popcorn method. And then you're going to solve the resulting quadratic or linear equation that you have. You have to check your answers into the original, and then obviously cross off anything that would produce a log of a negative number and 0. Okay, so with that being said, I know looking at this first problem here, the first thing I need to do is have only 1 log on this left side. So I combine them by using the product property. So I have ln of 6 times x minus 1, which is equal to ln of 3x. Well, using the uniqueness property, I know that I can drop the logs, and I'm left with, after I distribute on this left side, 6x minus 6 equal to 3x. So, if I subtracted 6x on both sides, I'd have negative 6 equal to negative 3x, divide by negative 3, and x equals 2. So before I box that, I want to make sure that I can have x equal 2. So if I were to put 2 right here in this first one, I'd have ln of 1, because 2 minus 1 is 1, and that's allowed. And over here, I'd have 3 times 2, that'd be a multiplication problem, which is 6. Neither are negative, neither are 0, so 2 is our solution. Okay, so for number 2, the same thing on this left side, we are going to combine them to write it as a single log, which is the product property. So I have log of 3 times x minus 7, which is equal to 2. I'm going to simplify this left side, and I get log of 3x minus 21. Not really simplifying, more like distributing. Okay, so now that I don't have a log equal to a log like I did on the left, so we can't use the uniqueness property. So we're going to use the other option, which is to rewrite it in exponential form. So since this log doesn't have a base, it's understood to be 10. So we have 10 to the 2 equals 3x minus 21. So now we just evaluate it and solve. 10 to the 2 is 100. And then our next step is to add 21 to both sides, so we get 121 equal to 3x, and we divide by 3. It doesn't simplify, so we get 121 divided by 3. Now, I'm going to, for the sake of checking, change this into a decimal, just so I can check it. I want, as your teacher, I want the exact answer, so leave it as the fraction, but for the sake of checking, I know that 21 over 3 is about 40. So if I plugged in 40 up here, I would have 40 minus 7, which is not going to give me a negative number. It's not going to give me 0. Since that's the only spot in the original that we can substitute it back in, that checks out that this is our answer, 21 over 3. Okay, so looking at number 3, I see that I have logs on both sides of my equal sign. So I can foresee that I'm going to use the uniqueness property, but before I can do that, and I can't cross out the logs unless it's a single log equal to a single log. So on this left side, I'm going to combine it by using the quotient property. So I'll have log of x plus 14 over x, which is equal to log of x plus 6. So now that I have a log equal to a single log, I can cross these out. So we have x plus 14 over x equal to x plus 6. Now, to get x out of the denominator, I'm going to multiply it by both sides. cancels out over here. Notice how I kept my parentheses over here because we will have to distribute. And we'll have x plus 14 equal to x squared plus 6x. So now we have a quadratic. So that tells us we're going to have two solutions, and before we can solve a quadratic, we need to set it equal to 0. So I'm going to pull everything over to the side where I have x squared because I don't want to solve a quadratic when my a value in x squared, the coefficient a, is negative. So since it's positive, I'm going to bring the x over here and the 14 over here by subtracting them from both sides. So I get 0 equals x squared plus 5x minus 14. So this can be factored and factors into x plus 7 and x minus 2. So then when we solve, we say x equals negative 7 and positive 2. Okay, now we have to check. So negative 7. If I plug in negative 7 up here for this x, that's good because I get positive 7, not negative number and not 0. But this is just log of x, so I can't plug in negative 7 there, which means this is not a solution. Negative 7 is extraneous. So now if I did the same thing, I need to do the same thing with 2. 2 plus 14 doesn't give me 0 or negative. I can take the log of 2, and I can take the log of 2 plus 6. So my solution is x equals to 2. And then over here, number 4. So number 4 has just one log. So again, we can foresee we're going to rewrite it in exponential form by rewriting it using popcorn. So I have to make sure that I only have one log. I can't have a number here. I can't have plus a number or variable over there. It has to be a single log, which this is. So there's only a log on this left side, so I can right away do the popcorn method. So we do 4 to the 2 equals x minus 10. 4 to the 2 is 16. And if I add 10 to the other side, x gives you 26. And if we check this answer, and I plug in 26 right here, 26 minus 10 is not a negative, and it's not 0. So this is our solution. Okay, so now some general rules for solving exponentials. You could take the log of both sides, which allows us to do the uniqueness property, or I added in, you can rewrite it as a log as well. So then we want to use the power law to move any exponents in front, and then we're going to solve for x, and for these we're going to use our calculators, and you'll see why in a second. So for number 1, let's just say I'm going to take the log of both sides. So I would take ln 8 to the x equals ln of 792. So what you do to one side, you have to do to the other. So now, again, I need to bring the power property into play and bring down the x. So we have x times ln of 8 equal to ln of 792. So I need x by itself, so now I'm going to divide both sides by ln 8. And this is where the calculator comes into play. So x equals ln of 792 divided by ln of 8. Just be sure in your calculator you use parentheses so you're telling it to do the right thing and what you want. So x equals about 3.210. Okay, so let's look at one where I don't take the log of both sides and I use the popcorn method or the rewriting method. So immediately right here, I can do that since I have just an exponential on the left. So I would rewrite it as log base 2 of 0.045 equal to negative x. So because I'm choosing to do it this way, now I can do the change of base. So I'm just going to switch the order. Negative x equals log of the numerator is always the first, the argument, 0.045, and then the base goes on the bottom, log of 2. So when you get this, you get negative 4.474, and since we have a negative over here, we would divide it and get x is about positive 4.74. 4.474. Now for these, you can check and do 2 to the negative 4.474 to get about 0.045, but you don't need to check it as far as like rules go, because you can have 0 in the exponent and you can have a negative number as an exponent. Okay, so for number 3, I'm going to do, let's rewrite this one, and then the next one we'll take the log of both sides. So for this one, I would say, okay, I have ln of 30, if I'm using the rewriting method, I need to take the log, because I have log base 2 of 30, which is equal to x plus 1. So here I would write log of 30 divided by log of 2. So when I do that, I have to remember I'm going to subtract 1. So you can even plug it in the calculator like this and say, okay, let's do log of 30 divided by log of 2. And then I'm just going to subtract 1 from it because I have this 1 over here. So x equals about 3.907. And then number 4, if we took the log of both sides, we would use ln. So we have ln of e to the x minus 1 equals ln of 15. Now we can bring that power down. And we know that the ln of e is 1 because it's e to the what gives me e. So it just turns into x minus 1 equals ln of 15. So you can plug 15 in your calculator, and then you would have to be sure to add 1 to it. So x is actually equal to ln of 15, and then add 1. So x is about 3.708. Okay, more practice. So I have a log and I only have 1 on the left, so I'm eventually going to rewrite it, but I can't do that until I get just a log on the left side. So the first thing I need to do is subtract 7, and I get negative 2 ln of x plus 1 equal to 0. Well, I would then divide both sides by negative 2, and that's simple because 0 divided by negative 2 is 0. Now, don't be alarmed that you're getting 0. 0 is a number. We can use it because look what's going to happen. ln has a base of e, so when I rewrite it, I'm going to say e to the 0 equals x plus 1. Well, what's e to the 0? 1. So we have 1 equal to x plus 1. Subtract 1 to both sides, x equals 0. Now, we're going to check our answer. Our answer is allowed to be negative, and our answer is allowed to be 0. It's more of the question, does the solution or my answer give me a log where I would have to take a log of a 0 or a log of a negative? And if I plug in 0 right here for x, which is the only place I can plug it back in, I would be taking the ln of 0 plus 1, which is 1. So this works. That's our solution. So for number 2, the first thing that sticks out is that we have 3 logs, but we have at least one on either side. So I'm going to condense this side so that I have just 1 log together. So I'm going to do the product property. So it's going to be log base 3 of x, and then I'm just going to distribute right here. So that's our new argument. So now that I have a log on either side, the uniqueness property cancels them out, and I have x squared plus 2x equals 8, but I'm going to subtract it over all in one step, and now I have a quadratic that I can factor. So when we get our solutions here, we need to check for negative 4 and 2. And the first thing that sticks out for me, I can't plug in negative 4 right here. That's not a solution. I can plug in 2, and I can plug in 2 here. And, well, on this right side, I can't plug in anything because there's no variable. So our solution is just x equals 2, because negative 4 is what we call extraneous. Okay, number 3. Again, we have a log on just one side, not on the other, so we're going to end up rewriting. But we have to condense it because we can't rewrite if we have 2 logs on one side. So this is the quotient property. Log base 2 of x divided by x minus 2 equal to 3. So we're going to rewrite it. Here we go. 2 to the third equals x over x minus 2. 2 to the third is 8, and I'm going to replace it since I'm running out of room. Now I need to get the x minus 2 out of the denominator, so I'm going to end up multiplying that by both sides. And I have to put parentheses because we are going to distribute this 8. And if I added 8 to the other side, I get negative 16 equals negative 7x. So x equals positive 16 over 7. And for the sake of checking, if I did 16 divided by 7, I get 2.2. And I can plug that in here. I can plug it into this right side because since it's greater than 2, it's 2.2857. And if I subtract 2, I'm going to get a decimal, but it's not negative and not 0, so that's okay. And I can also plug it in here. So this is our solution. Number 4, again, log on both sides. So I'm going to condense this left side with the product property. And I'm going to get log of 3x minus 6 because I'm going to distribute all in one step equals log of 5x minus 7. So since we have the log on both sides, log cancels out. And we have 3x minus 6 equal to 5x minus 7. So if I take the 5x over to my right side, I get negative 2x. If I add 6, I get negative 1. So x equals 1/2. Okay, so if I plug in 1/2 right here, I have 1/2 minus 2, which gives me a negative. And all of a sudden, I don't have to check any further because that's enough for me to say, nope, that's extraneous. And when we only have one solution because it was linear, then we respond and we say no solution at all because the one we found was extraneous. So no solution for number 4. Okay, and our final 2 problems are exponentials. So I'm going to rewrite this as a logarithm. So I have log, and I don't even need to write base 10 because it's understood, of 1/2 equals x over 2. Well, I can take log of 1/2, but to be even more exact, I'm going to multiply both sides by 2. And since that cancels on the right, x then equals 2 times log of 1/2. Now, please note that it is the log of 1/2. Please don't put a 2 up here and say, oh, that's the log of 2 over 2, which is 1. No, that's not it. You're taking 2 times the log of 1/2. Very different. So when you do this, x equals about negative 0.60, that was about 2. And then my last one, number 6 over here, I can't rewrite until I have just an exponential. So my first step is dividing both sides by 10. So we have e to the 2x equals 40. Now I can rewrite as a log, I'm going to use ln. So ln of 40 equals 2x. And just like on that last one, I'm going to divide by 2 first. So x actually equals ln of 40, put parentheses around that, then divide it by 2, so x is about 1.844.